Hi, it's me, Marcel. So, initially, I tried to record this presentation with Zoom, but for some reason, it did not record the audio. So, I lost 15 minutes of my first presentation. So, I'm using Twitch this time. I'm going to be streaming this magnificent presentation. Okay, so this was my original plan. So, I had the box jump. I'm doing a box jump study for my dissertation, and the idea was to collect the data from the Pascal force plates, and whenever you do that, you get a CSV file, and that's why my flowchart starts with that. So I'm gonna read from the file, the CSV file that it's generated by the Pascal. From that, um, I'm not sure if I have to do this. I read some papers that show like it's that tell that you should be fine when you're working with raw, just with the raw data, no filtering. So I'm not going to be doing this at this time, but this is something that can be easily fixed. From the file, I will determine the body mass of the subjects. And one of the most important things is to determine the onset and offset of the movement so I can analyze different jumps from the beginning and the end of the movement. And those points over here that I delimited, it's what it's set in the literature. So everything has been validated already. I also plan to normalize everything based on body mass and also by time. So from 1 to 100%, because that's something that I'm planning to do later is to do this statistical parametric mapping, SPM. And to do that, I need to normalize the data. So they all have the same size. They all range from 0 to 100%. And I'm going to show the graphs that actually show that, how they look like. From the CSV file, I plan to calculate the impulse, acceleration, center of mass velocity, power, center of mass displacement, and rate of force development. That was my initial plan, and I'm going to show you what I did. Um, so the first thing that I did, like I said, was to determine the onset and the offset. So whenever I select the CSV file from Pascal, the pilot file over here, I open and I run, it will give me a raw data file and we will also save it, and also a process data file with already the onset and offset delimited. And there's, like we discussed before, the LabVIEW adds some zeros at the end, and that will be a problem if I am going to calculate acceleration mean values specifically, because if you have a lot of zeros, it's going to affect the mean values a lot. So I'm going to show you what I did to fix this issue. But something that can be done is to do the normalized graph. When I did from 0 to 100%, it excludes the excess of data at the end. The one problem is you cannot save it through LabVIEW, but I found this fix when you can export to Excel, and it creates a temporary file with everything. So ranging from 0 to 100%. Each jump individually, so 100%, 100%, and 100%. And it does not add the zeros at the end. So if I'm doing any analysis after this, it would be really helpful to have this. Okay, so this is how the my block diagram looks like. I'm gonna explain this very briefly, mostly because it's this my second time explaining this. But initially, I have the Pascal GRF file, and this is the file. So I excluded this row with the titles, and also for this first part, I do not need time, so I'm going to be looking at 1, 2, and 3. And as you can see right here, I have 1, 2, and 3. So from all of that, I determined the first thing I did to calculate body mass. So I took the first 400 milliseconds. The mean of that was used to determine body weight in newtons from each participant. And after dividing that by 9.8, I got the body mass in kilograms that I'm going to be using later for some of the variables. The onset of the data was set as 5 standard deviations from the body weight that I delimited. Also, and that's what has been validated in the literature. And the offset was whenever the GRF reaches values of 5 or less than 5 at the end, also validated. And to do that, I created this while loop. Um, I created while loops for each jump. I set the onset as I just mentioned. To do the offset, I flipped the data. I found the value that was greater or equal to 5, and then I reflipped, unflipped the data, and then I found the offset of each one of them. To do the normalization, I got the sample array size, and I wanted to have all the data distributed from 0 to 100% equally. So I use this ramp by samples, and that's why you can see right here on this normalized X and Y graph. So from here, I was going to calculate all the variables, but I found a problem. When I was looking for papers, it is more acceptable now if you have to divide the jump through the 3 different phases of the jump before you analyze, so you can analyze each of those phases individually. So I figured I would have to do that before calculating anything. So I created another VI just for the phases breakdown with 3 phases: unweighing phase, braking or eccentric, and propulsion or concentric phase. I also start this by opening the process data that is saved by after the other VI. So we have a process data, sorry, and the CMJ phases file that's going to be generated at the end of this, and I'm going to be using for the next phase. So I have all the jumps set in phases. I also normalized just in case I want to analyze the jump, each phase of the jump, and compare that to other jumps. I can have all the curves from 0 to 100%. That's something I intend to do in the future. The block diagram of this one is a little more complicated because I had to set the onset and offset of each phase. Uh, I use the process data that I saved on the first VI, the first 3 columns. So each column will be a one while loop over here. The unweighing phase, it was the easiest one because it's from body mass. So I told LabVIEW, whenever you get anything, the next data point that it's zero point 0.1 greater or equal to the value that we had for body weight, it's going to be the end of the unweighing phase. And as you can see right here, it was about 920 and probably 921 over here. That was the end of the unweighing and the start of the eccentric phase. That is just going uphill, and that made my life very simple. To do that, I calculated the next 400 milliseconds after the unweighing phase, and when I look at the to find that number, I checked individually. So 400 milliseconds from here would be around this loop over here. So we still have plenty of space, and it worked for every single jump because all the jumps, they have very similar patterns. And to find the end of the eccentric phase, it's the highest value over here, the peak. So we still have a lot of room. I ran through several different jumps and it worked. So I found that peak. So whenever we reached the peak value from those 400 milliseconds after the unweighing phase, that was the onset uh, and offset of the braking or eccentric phase. The concentric phase was from the end of the braking phase towards the end. And I'm going to be using also the peak value to calculate other variables. Uh, all of those were saved in an array named phases file, and I also have the normalization of the data here for further analysis. So, and that brings us to the tricky part. The VI, the key variables identification. Because I saved everything on the CMJ phases file, LabVIEW added the zeros at the end. And that would mess everything from now on, especially when it comes not much to the peak values, but to the mean values, because it added a bunch of zeros at the end. So the first thing that I did for all of the columns that I've saved, for all the three phases, three different jumps, so all the 9 columns over here, I flipped it down and I told LabVIEW like I only want values that are greater or equal than zero point 0.1. That would exclude all the zeros. I troubleshoot troubleshot this and it worked. And it has a nice design over here. So I created subarrays without the zeros at the end for each of the jumps. I unflipped the data set, and that's how I calculated all the variables over here. So I calculated peak force, mean force, and relative peak force and mean force for all three phases and all three jumps. So we have a total of 6, 12. So we have 36 columns in this array right here, just for peak force and mean force. I also I have this again. I plan to turn this into a VI, the body mass determination VI, so I don't have to do all of those calculations over here. That's something that I plan to do to make it more simple. But I calculated the body mass again because I'm going to need this to calculate acceleration and impulse. So from the same data set, I same calculations that I did on the first VI, and I use those numbers to I multiply the force time data by the time. This time I'm actually using this column over here, time, and data was collected in 1,000 hertz, so each data point will be 0.001. Let me go back to, oh, that's the wrong one, this one. So I actually use time, so I multiplied force uh, times time, and I divided by the body weight. That's what I did here to calculate acceleration. And it has its own array because I still need to double check everything to make sure I did the right calculations. But once I'm done with everything on this VI, I'm planning to make a single massive array with all of the variables that I calculated and with the titles. That will make my life much easier when I export everything to SPSS to run the statistics. The last thing that I did, and it was a little bit more work because I had to integrate the GRF file in order to find the center of mass velocity, the impulse momentum, or forward dynamics in biomechanics. In order to do that, I had to use. I was trying to do everything manually at the beginning, and it was a lot of work. And then I realized there's a VI that does that. So integral, I used the trapezoid rule because that's again validated and accepted in the literature. So trapezoidal rule. My This is how I was calculating data. So the time samples, they were all 0.001. Using the GRF file, I calculated the center of mass velocity, and just for the sake of curiosity, I was testing to see the max values. So to see if the peak values they look like the values that we usually find in the literature, just to make sure that I did the right calculations over here. And I have the graphs and the values over here. So the unweighing phase, it's not usually reported, so I couldn't find it anywhere. But for the eccentric and the concentric phase, oh, I didn't want to move that. The curves, they look very similar, so I guess they are right. But when I look at the values are basically the same. So I would say if uh, the formula or what I did here with the VI was right, and that's what I intend to do next was to use that value to calculate center of mass displacement. And we can also calculate jump height with these values. But I haven't done that right. That's what I'm planning to do next. Uh, Especially the concentric value, it was on the dot the same value that I found in the literature, 2.67 at the end of the concentric phase. So this is what I have so far. Uh, I got some really nice pyramid shaped uh, nodes or wires, and I was able to calculate everything that I wanted to do so far. But because I was double checking everything, it took me a lot of time. I also did this so I can actually see the numbers, see if I see any wonky numbers before I save the data and I calculate the other variables. So I thought that would be helpful. I plan to add the acceleration values over here, center of mass velocity, and center of mass displacement, and rate of force development values over here as well. So this is everything I have so far, and I will still be working on this. And something that I didn't mention was I did all I did this inside a box case structure. I was trying to remember the name, and I'm planning because I have five different conditions, and for each condition, three jumps. So I'm planning to have instead of having a massive VI, I'm gonna just change the pages. So from trials 1 to 3, 4 to 6, 7 to 10, and so on. So I'm planning to do this for all the trials. So I can change this later because it was a lot of phases for a lot of jumps. I wasn't expecting to have to do this, but that was really helpful, and I found out how to do it. Well, that's it. I will be submitting all the files, and hopefully this was good enough.